Alright, in this video we're going to talk about doubling time and half-life. Doubling time and half-life. That's section 8b. Now we're going to begin this section with a quick review of what they call logarithms. Okay? Let's talk about what logarithms are. Okay? Now a logarithm, or log, or log for short, is a power or exponent. So here we're going to be focusing on base 10 logs, also called common logs or common logarithms, which are defined as follows. In this case here, if you have log to the base 10 of x, that means the power of 10 that makes x. So here you're going to find out the exponent where log to the base 10 is equal to, of x will equal. It means 10 to what power will give you the x. Like, for example, log of 1,000 to the base 10 will give you 3. The reason for that is you want to find out 10 to what power will give you 1,000. And that's, of course, 3. Because 10 cubed is 10 times 10 times 10, which is 1,000. Also, log to the base 10 of 10 million. That's going to equal to 7. And that means, in this case here, 10 to what power will give you 10 million, which would be 7, because 10 to the 7th power will give you 1,000. Also, log to the base 10 of 1 will give you 0. And that's because 10 to the 0 power will give you 1. Also, log to the base 10 of 0.1, that's going to be negative 1. Because if you think of it, 10 to the negative first power will give you 0.1. And also, log to the base 10 of 30 will be approximately 1.477, because 10 to the 1.477 power will be approximately 30. Now here you can use your calculator, the graphing calculator, to find out the common logarithms, because on the left hand side you're going to see the log button that's on the left of number 7. So if I press the log key, then you're not going to see a base 10, but your calculator understands it to be base 10. And if I type in 1,000, let's say, for example, you'll get the 3, because it'll give you the 3. That's the exponent where 10 to the third will give you 1,000. And log of 10 million, that will give you 7. And where they got that 1.477 for log to the base 10 of 30, press the log key and then type in 30. And that's to 3 decimal places, approximately 1.477. Okay. Now, there are 4 important rules that follow directly from the definition of a logarithm. Okay. We're going to go over these. So in this case, rule number 1, if you take the log of a power of 10, it gives the power. Like, for example, here in this case, log to the base 10 of 10 to whatever your exponent is, it's going to be that exponent. Okay? Log to the base 10 of 10 to whatever your exponent is will be that exponent. So let's say I have something like log to the base 10 of 10 to the 6th. The log to the base 10 and the base 10 itself are what we call inverses of each other. So log to the base 10 of 10 to whatever your exponent is that exponent. In that case, it's going to be 6. Rule number 2, raising 10 to a power that is the logarithm of a number gives that number. In this case here, 10 raised to the log to the base 10 of x is that number x. The restriction here has to be where x is greater than 0. So if I had something like 10 raised to the log to the base 10 of, let's say, 8. 10 and log to the base 10 are inverses, so I can apply rule number 2 and say 10 to the log to the base 10 of 8 would be 8. And then rule number 3. Because powers of 10 are multiplied by adding their exponents, we have the addition rule for logarithms. If you have the log to the base 10 of the product of these two numbers, x and y, and x is positive and y is positive, we can write that as a sum of their individual logarithms, log to the base 10 of x plus log to the base 10 of y. Okay, so when you have the log of a product, we can write that as a sum of their individual logarithms. And then rule number 4, we can bring down, in quotes, an exponent within a logarithm by applying the power rule for logarithms. Like here, if you have log to the base 10 of a to the power of x, here that x is your exponent, we can pull that exponent in front, and it'll be multiplied by log to the base 10 of a. And of course, a has to be a positive number. Okay. All right, next, most calculators have a key to compute log to the base 10 for any positive number, which I just showed you. You should find this key on your calculator and use it to verify that log to the base 10 of 1,000 is 3, and log to the base 2, log to the base 10 of 2 is approximately 0.301030. Okay, now I do have some examples here that we can look at here on the first page of your handout. Given that log to the base 10 of 2 is equal to 0.301030, find each of the following. Like in part A, log to the base 10 of 8. And here it is right here. That 8 is a base of 2. Well, it is a multiple of 2, so we can write that as 2 to the third power if we want to. So log to the base 10 of 8 would be log to the base 10 of 2 to the third power. Now there is that power rule, which is rule number 4 that I went over. We can pull that exponent of 3 in front. So it'll be 3 times log to the base 10 of 2. And we're given that log to the base 10 of 2 is 0.301030. Okay? And this is a mistake that they made here. That 10 should be a subscript, not a superscript. So it'll be 3 times 0.301030, or approximately 0.90309. That's the approximate value of log to the base 10 of 8. Now for part B, we got 10 raised to the log to the base 10 of 2. Well, that follows rule number 2 right here, where if you have log to the base, well, if you have 10 of log to the base 10 of whatever that number is, or whatever that is, it's going to be whatever that is. So here, 10 raised to the log to the base 10 of 2 will be 2. And then part C, log to the base 10 of 200. Well, 200 can be written as 2 times 100, or 2 times 10 to the second. Okay, so here, using rule number 3, we can write that as the log of the product, the log to the base 10 of 2 times 10 squared. Now, rule number 3 says, if we have the log of the product, we can write that as a sum of individual logarithms here, which will be here, log to the base 10 of 2 plus log to the base 10 of 10 to the second. Now from rule number 1, log to the base 10 of 10 to whatever your exponent is going to be that exponent. since log to the base 10 of 10 squared, that's going to be 2. Here we can write that as log to the base 10 of 2. Well, we can write it like this. But here, log to the base 10 of 2, that's the 0.301030 plus the log to the base 10 of whatever that exponent is, in this case it's going to be 2, would be that exponent of 2. Add those two together, you're going to get 2.301030 as the final answer. Okay, and here's another example here on the far right. Someone tells you that log to the base 10 of 600 is 5.778. Should you believe that? Okay, in this case here, 600 is going to be between two numbers that are powers of 10, 100 and 1,000, because those are powers of 10. So that means log to the base 10 of 600 has to be between log to the base 10 of 100 and log to the base 10 of 1,000. Well, log to the base 10 of 100, if we write that in exponential form, 100 is 10 to the second. So we can write that as log to the base 10 of 10 squared. And using that first rule, we can say log to the base 10 of 10 squared will be 2. And log to the base 10 of 1,000, I can write 1,000 as a power of 10, which is 10 to the third. So log to the base 10 of 10 cubed, again using that first rule, will be 3. That means that log to the base 10 of 600 has to be a value between 2 and 3. And they're telling you that log to the base 10 of 600 is 5.778. So here that claimed value has to be incorrect, because it must be between 2 and 3. Okay, let's start this with some examples. Here we're going to determine whether the following statement is true or false without doing any calculations here. Like 10 to the negative 1.831 is between 0.01 and 0.1. Now let's think about this for a moment. If I write 0.01 as in exponential form, I know 0.01, that's going to be 1 over 100, because there are two numbers behind the decimal point. And I know 100 in exponential form has to be 10 squared, or 10 to the second. And if I write that with negative exponents, here I take the 10 out of the denominator and change the 2 to negative 2. So 0.01 will be 10 to the negative 2 power. And then 0.1, that's 1/10, or 1 over 10, because there's one number behind the decimal point, so it'll be a 1 with a 0 in the denominator. And of course 10 is 10 to the first. And if I write that with a negative exponent, I'll pull the 10 out of the denominator, that 1 becomes negative 1. Okay? So that means 10 to the negative 1.831 has to be between 10 to the negative 2 and 10 to the negative 1. And this is actually true, because if you look at it, between negative 1 and 2, or negative 2 and negative 1, negative 1.831, if you look at that exponent, it does fall between negative 2 and negative 1. That statement is true. Okay. Our second example. 10 to the negative 4.6 is between 0.00001 and 0.0001. Is that statement true or false? Okay, well, I know 0.0, 4 zeros and then followed by 1. If I was to write that as a fraction, that would be 1 over a 1 with 5 zeros because there are 5 numbers behind the decimal point. And this will be 1 over 10 to the, there are 5 zeros, that will be 10 to the 5th. And if I write that with negative exponents, it would be 10 to the negative 5. Pull the 10 out of the denominator, the 5 becomes negative. And then 0.0001, that's going to be 1 over a 1. There are 4 numbers, there are 4 digits after the decimal point, so it'll be 10,000. So it'll be 1 over 10,000. 10,000 in exponential form will be 10 to the 4th, because there are 4 zeros in 10,000. That's why it's 10 to the 4th. And then as a negative exponent, it would be 10 to the negative 4. So if we look at 10 to the negative 4.6, and then look at 10 to the negative 5, and then 10 to the negative 4, you can see here that if we look at your exponents, negative 4.6 is between negative 5 and 4. Okay? So this will be true because 0.00001 will be 10 to the negative 5th, and then 10 to the negative 4th will be 0.0001. Okay. Now let's look at example 3 that deals with the logarithm. The log to the base 10 of 15 million is between 7 and 8. Okay. Let's see how we're going to do this one. We have to find 2 numbers that are powers of 10 that's less than 15 million and greater than 15 million. Okay? Here I know 15 million is between, we know it's greater than 10 million, but it's less than, we have to do another power of 10, 100 million. 10 million and 100 million. I know 15 is between 10 and 100. Those are powers of 10. So in millions, 10 million and 100 million would be the ones we have to use here. So that means 15 million, if I take log to the base 10 of 15 million, it has to be between this, the log to the base 10 of 10 million, log to the base 10 of 10 million, and log to the base 10 of 100 million. Because I'm adding the logarithm here for each one of those. Now we can find log to the base 10 of 10 million. Because if I write 10 million in exponential form, this will be this. I have log to the base 10 of 10. Count how many zeros you have here. That will be your exponent for 10. In this case, it's 7. And I'm going to apply that rule where if you have log to the base 10 of 10 to whatever your exponent is, it's going to be that exponent. So log to the base 10 of 10 to the 7th is 7. And then I'm going to do log to the base 10 of 100 million. So here log to the base 10, and then that's going to be 10 to the 8 zeros, so it'll be 10 to the 8th. And if I do log to the base 10 of 10 to whatever my exponent is, it will be that exponent. Okay? So here it says here log to the base 10 of 15 million is between 7 and 8. Well, is that would be exactly true right here, because I came up with 7 and 8 for log to the base 10 of 10 million and log to the base 10 of 100 million, respectively. So this will have to be true. Okay. All right, here's another example of this. Determine whether the following statement is true or false without doing any calculations here. Here we got log to the base 10 of 3/8 is between -1 and 0. I'm going to write 3/8 as a decimal. So if I do 3 divided by 8, I'm going to get 0.375. And I can see that 0.375 is between -1 and 0. So I'm going to write like this. -1 is less than the 0.375 and less than 0. Well, I tell you what, I won't write like this. Okay. Let's take that back. Let's start over. Okay. Because I need to find what decimal powers of 10 is 0.375 between. I know it's less than 1, because 1 is a power of 10. And I know it's greater than 0.1, because 0.1 is actually 1/10, or 10 to the -1. That would mean if I take the log on the left side to the base 10, on the left side and in the middle, and on the right side, that means log to the base 10 of 0.375 has to be between log to the base 10 of 1/10 and log to the base 10 of 1. Okay, now if I take log to the base 10 of 0.1, that's actually 1/10. And if I do log to the base 10 of 1, well, I know this is 10 to the 0 power, because the only number where 10 to what power would give me a 1 will have to be 10 to the 0 power, because 1 will be 10 in the base 10. Anything to the 0 power except 0 has to be 1. Okay? Now, log to the base 10 of 1/10, if I write that in exponential form, 10 to the -1. Now, if I do log to the base 10 of 10 to whatever that exponent is, it's going to be that exponent. So log of 10 to the base 10 is 0. Now here, the same thing here. Log to the base 10 of 10 to that exponent will be that exponent, in this case, -1. Now what this is saying is log to the base 10 of 0.375 is between -1 and 0. That's exactly what this statement says. So that's going to be true. Okay. Now, if all of that was confusing, you could use the calculator and then press the log key and then do 3 divided by 8. You'll see it's a -0.4295. That is between -1 and 0, so that would be true. But here I'm just doing this, so showing you how you can do this without having to use a calculator for this. Okay? But you are free to use the calculator if you like. Okay, let's look at this example 5. Here we're going to use the approximation of log to a base 10 of 6 is approximately 0.778. to find each of the following without a calculator. So starting with part A, we got log to the base 10 of 36. Log to the base 10 of 36. Well, I know that 36 is going to be a multiple of 6. Because 6 times 6 is going to be 36. 36 will be 6 to the second, so I can write 36 as 6 squared. So it'll be log to the base 10 of 6 to the second. Okay? Because 6 squared is 36. I also can apply a rule that says if I have an exponent up here, I can pull that exponent in front of the logarithm. That's the power rule that I talked about on the very first page. So I can pull the 2 in front. So it'd be 2 times log to the base 10 of 6. Okay. So here, 2 times log to the base 10 of 6 is that 0.778. So I'm going to multiply 2 times 0.778, and you will get 1.556. That will be what log to the base 10 of 36 will be equal to, 1.556. Okay, part B, log to the base 10 of 6,000. Okay, now I can write 6,000 as 6 times 1,000 here. So that's what I'll do here. I'll write this as log to the base 10 of 6 times 1,000. Now, there's a rule that I talked about where if you have the log of a product, we can write that as addition, okay? We can write that as the sum of the individual logarithms here. So log to the base 10 of 6 times 1,000, I can write that as log to the base 10 of 6 plus log to the base 10 of 1,000. Okay. So in this case here, log to the base 10 of 6, I'll just bring that over. But 1,000 can be written as 10 to the third, so I'll have the log to the base 10 of 10 to the third. Because notice in 1,000 I have 3 zeros. So in exponential form, it would be 10 to the third power. Okay. Now, I'm going to use the fact that log to the base 10 of 6 will be 0.778. And for log to the base 10 of 10 to the third, I'm going to use the rule where you have the log to the base 10 of 10 to whatever your exponent is, it is that exponent. So log to the base 10 of 10 cubed would be 3. So add 3 and 0.778 together, you're going to get 3.778 as the final answer. All right, part C, log to the base 10 of 1 over 36. Okay, I'm going to have to do this down here. So in this case here, log to the base 10 of 1 over 36. Well, 36, I can write that as a base of 6, as 6 times 6, or 6 to the second. So here I'm going to have log to the base 10 of 1 over 6 squared. But I can write that with a negative exponent. Pull the 6 out of the denominator and make the 2 negative. So I have log to the base 10 of 6 to the negative 2 power. And then apply that power rule where you pull the exponent in front of the logarithm. So this will be negative 2, put the exponent in front. That'll be times log to the base 10 of 6. So here, negative 2, bring that over. And log to the base 10 of 6 is going to be approximately 0.778. So negative 2 times 0.778 will be negative 1.556. Okay, so that's what log to the base 10 of 1 over 36 will be. And part D, we got log to the base 10 of 0.06. Okay. I'll also do this one down here. Log to the base 10 of 0.06. I'm going to write 600 as a decimal. I mean as a fraction. It's already a decimal. I just want it as a fraction. 0.06 will be 6 over, the two numbers after the decimal point has to be 100. So that will be 6 over 100. Okay. But 100 is a power of 10. I can write 100 as 10 to the second. So we log to the base 10 of 6 over 10 to the second. Now in this case, that 10 to the second, I'm going to pull that out of the denominator. So this will be, in this case, 6 multiplied by 10 to the negative 2. The 10 comes out of the denominator. Your exponent of 2 will be negative. Okay. In this case here, I have the log of a product. I can write that as the sum of their logarithms. Okay. So this will be written as log to the base 10 of 6, and then plus log to the base 10 of 10 to the negative 2. Okay, log to the base 10 of 6 was, need to pull this down, it is given as 0.778. Add to it, log to the base 10 of 10 to whatever my exponent is, it is that exponent. In this case, negative 2. So if I add 0.778 to negative 2, I'm going to get negative 1.222. And that will be a final answer to that problem. Log of 10 to the 0.06. Okay. So that's just a quick review of what logarithms are and how to do those. Okay. Next, we'll talk about doubling and halving times. The time required for each doubling in exponential growth is called doubling time. And the time required for each halving in exponential decay is called halving time. Halving time. Okay, we'll talk about doubling time first. After a time called t, an exponentially growing quantity with a doubling time of t sub double increases in size by a factor of 2 to the t divided by t sub double, a new value of the growing quantity is related to its initial value at t sub t equal to 0 by this formula. The new value will be equal to the initial value multiplied by 2 raised to the t divided by t sub double. Okay, t sub double, of course, is the doubling time. Lowercase t is the time itself. Okay, so now let's look at a few examples of this. All right, example 6, if I can pull the paper up. The doubling time of a population of flies is 8 hours. By what factor does the population increase in 24 hours? By what factor does the population increase in 2 weeks? Now let's identify what we already have. It tells us the doubling time of a population of flies is 8 hours. That is what T sub double is. 8 hours. And we want to find out by what factor does the population increase in 24 hours. In this case, that's going to be lowercase t, 24 hours. So to find that out, we use that 2 to the t over t sub double. Now that exponent is a fraction, so it's 2 to the t divided by t sub double. So this will be 2. And for your exponent, the t, lowercase t, is 24. Divided by t sub double, that's your 8. Now if we simplify the exponent, what's 24 divided by 8? That will give you 3. So this will be 2 to the third power. So by what factor does the population increase in 24 hours? Now here they want the exponential notation with positive exponents here. 2 to the third. Okay. That's how we answer that question. Now, by what factor does the population increase in 2 weeks? Now, the doubling time is given in hours, but here the time is given to us in weeks. Our unit of time has to be consistent. Okay, since t sub double is 8 hours, we need to convert the time in hours as well. Okay, you do need to know that in 1 week, there's 7 days. So we're going to multiply 7 days for 1 week. And then times, now we still need to convert for hours. Now, in 1 day, we have 24 hours. That's 24 hours in a day and 7 days in a week. So here the weeks divide out and the days divide out. And we multiply 2 times 7 times 24 on your calculator. You will get 336 hours. And we had to convert to hours for our time because t sub double is in hours. Okay, the unit of time has to be consistent. Okay, and now we can use this formula, 2 raised to the t divided by t sub double, to find out what our factor is, that the population increases in 2 weeks. So here this will be 2, lowercase t, that's 336, divided by t sub double, that was 8. So this will be 2 to the, if I do 336 divided by 8, I will get 42. So in this case here, by what factor does the population increase in 2 weeks? It will be 2 to the 42nd power. And again, they want that as an answer in exponential notation with positive exponents. Okay, so you want to be very careful on how they want you to type in your answer when you're doing the homework. Okay, all right, let's look at example 7. The doubling time of a bank account balance is 11 years. By what factor does it grow in 44 years and in 66 years? Okay, and here they want us to simplify our answer. Okay, so in this case here, your t sub double, that's the doubling time, is 11. And we want to find out by what factor does it grow in 44 years. So here your t is going to be 44. Now we don't need to convert this because the doubling time is in years and the time itself that we're given is also in years. Okay, so now you're going to have 2 to the lowercase t divided by t sub double. That will be 2 raised to the lowercase t is 44 divided by t sub double, that's 11. Take 44, divide that by 11, you're going to get 4. So it'll be 2 to the 4th. And on the calculator, you can do this by doing 2, hit the hat key for your exponent, and then 4, and then hit enter. You'll get 16. Here they want the simplified answer. So by what factor does the balance grow in 44 years? By a factor of 16. And then by what factor does the balance grow in 66 years? Now this time, your t is going to be 66. And t sub double will still be 11. So here we're going to be using that factor of 2 raised to the t divided by t sub double. So it'll be 2, and then your t is going to be, lowercase t is 66, divided by t sub double, that's 11. And now 66 divided by 11 will be 6. So 2 raised to the 6th power will give you 64. So the balance in 66 years will grow by a factor of 64. Okay. That's how we do example 7. Okay, example 8. The initial population of a town is 3,500, and it grows with a doubling time of 10 years. What will the population be in 12 years? Okay, so now let's identify what we have here. The initial value, or the initial population, is 3,500. And it has a doubling time of 10 years. That's what t sub double is, equal to 10 years. And we're finding out what will be the population in 12 years. That's lowercase t. Okay, now that's where we use this doubling time formula. New value is equal to the initial value multiplied by 2 raised to the t divided by t sub double. New value is equal to the initial value times 2 raised to the t divided by t sub double. And we just substitute into that formula. The initial value was 3,500. Multiplied by 2 raised to the lowercase t, that's 12, divided by t sub double, that's going to be 10. And we're going to give this answer to the nearest whole number as indicated here. Now we can type this in as 3,500 times 2, and then the hat key for your exponent, 12 divided by 10, and then hit enter. So to the nearest whole number, I'm going to get 8,041. So the population in 12 years would be 8,041. Okay, let's look at this next example. In 2013, the estimated world population was 7.1 billion. Using a doubling time of 49 years to predict the population in 2028, 2063, and 2116. Okay, so we're going to be using that doubling time of 49 years. Now, we have an initial value. I'm just going to say 7.1 because if you look at the prompts where you'll be typing in your answer, they have the word billion behind it. So we'll just say 7.1. We know it's 7.1 billion, but we're using just 7.1 as our way to work these problems out. The doubling time is 49. So t sub double is 49. So now, in 2028, your t is going to be that year 2028 minus 2013. That's going to give us 15. So your t is going to be 15. Okay, now, to find out what the new value is, that's equal to the initial value times 2 raised to the t divided by t sub double. Your initial value was 7.1 times 2 raised to the t, lowercase t, that's 15, divided by t sub double, that's 49. So using the calculator, we do 7.1 times 2 raised to the 15 divided by 49. And they want this to 1 decimal place. So to 1 decimal place, this will be approximately 8.8 billion. So the population in 2028 will be approximately 8.8 billion. Okay. And then what will the population be in 2063? Okay. Our initial value is still 7.1 and t sub double is still going to be 49. So here, lowercase t, this time it's going to be 2063 minus the 2013. Okay. So 2013 from 2063 will be 50. So the time would be 50. Okay. And I'm still going to use this formula right here, the new value, and I'm not going to write it again. The new value is the initial value, which was 7.1 times 2 raised to the lowercase t, that's 50, divided by t sub double, that's 49. So here we're going to do 7.1 times 2 raised to the 50 divided by 49. Then hit enter. To 1 decimal place, that would be approximately 14.4 billion. So the population in 2063 will be 14.4 billion. And then what will the population be in 2116? Okay, so let's find out what t, lowercase t, will be. Subtract 2116 minus the 2013. You'll get 103. So your time is going to be 103 this time. And in this case, the new value, using the same formula up here, that would be the initial value of 7.1 times 2 raised to the lowercase t, this time is 103, divided by t sub double, that's 49. So here I got 7.1 times 2 raised to the, use the hat key, 103 divided by 49. And this will be approximately the one decimal place, 30.5 billion. So in 2116, the population will be approximately 30.5 billion. Okay. All right, let's look at this right here, the approximate doubling time formula. The approximate doubling time formula, which is going to be used for the rule of 70. Okay, for a quantity growing exponentially at a rate of capital P percent per time period, the doubling time is approximately this formula. T sub double is approximately 70 divided by P. Now you're not going to convert the percent to a decimal. You'll take that percent as is, and you'll do 70 divided by that. Now this approximation will work best for small growth rates, but breaks down for growth rates at over about 15%. So if it's less than 15%, it would work. But over that amount, then that formula will start breaking down. All right, take a look at example 10. In this case, we got a community of rabbits. It begins with an initial population of 105 and grows 5% per month. Make a table that shows the population for each of the next 15 months. Based on the table, find the doubling time of the population and briefly discuss how well the approximate doubling time formula works for this case. Now here I know that the population growth, that's 5% per month. Okay. Now we know that the population increases by 5% per month. That means your population growth, that's going to be this number, 1.05. Because 5% as a decimal will be 0.05. And we have to add that to the initial population here. So it's got to be 1 plus that 5% or 1.05. So it'll be 1.05 times its previous value. Okay. So the initial population is 105. So after 1 month, after month 1, we're going to have this 1.05 times 105. Okay, you're going to do that on the calculator. That will give you 110. So after the first month, the population will be 110. And then after the second month, it's going to be 1.05 times the previous value of 110. And I'm going to round each one of these off to the nearest whole number. So when you do these, you're going to get decimals, but they say round to the nearest whole number. And in this case, you'll get 116. So after the second month, it'll be 116. After the third month, we take that same 1.05 times the previous number of 116. It'll be 122 after the third month. Now, after the fourth month, 1.05 times the previous number of 122, that will give you 128. So after the fourth month, it'll be a population of 128. Then after the fifth month, we take 1.05 times 128. That's the previous number, which would be 134. Okay, and we keep doing this all the way up to the sixth month. 1.05 times 134, that'd be 141 rounded. And then the seventh month, 1.05 times 141, which is the previous month, 148. Okay, pretty much you just type this in the calculator, you'll get that number to the nearest whole number. Okay, now on the next page, we're going to continue this for the remaining 8 months. Okay? So in month 7, it was 148 for that population of rabbits. So to find the population in month 8, we're going to do 1.05 multiplied by the previous month of 148. You'll get to the nearest whole number, 155. And then month 9, the same thing, 1.05 times, this time 155. We're taking the previous month. This will be 163. Month 10, 1.05 times 163. This will be 171. And again, we're rounding to the nearest whole number in all of these situations here. And then month 11, 1.05 times 171 gives us 180 approximately to the nearest whole number. Month 12, 1.05 times 180, that's 189. And then month 13, that'll be 1.05 times 189. I'll get 198 to the nearest whole number. Then month 14 will be 1.05 times 198. That's the previous number. This will be 208. And then 1.05 times 208 will get 218. So here our table is complete. Okay. Now I'm doing this quick because of time. Okay. Now, based on the previously calculated data, determine the doubling time of the population. Okay, so in this case here, to find out what the doubling time is, T sub double was that formula 70 divided by P. That's the approximate doubling time. Okay, so I'm using this formula here. T sub double is approximately 70 divided by P. Now, the growth rate was 5%. That's your P. So, if I do 70 divided by 5, that's going to be approximately 14. Okay? Now, to answer this question, the doubling time of the population is between what two numbers? Well, we started off with 105. If you double it, it's going to be 210. Now, we need to look on this table to find out where 210 falls. Well, it falls between 208 and 218. And we need to look at the months where we got 208 and 218. For 208 is the month number 14, 218 is month number 15. So that doubling time is going to fall between the 14th month and the 15th month. So that doubling time of the population is between 14 and 15 months. And then discuss how well the approximate doubling time formula works for this case. Okay, in this case here, that doubling time formula does work well to approximate the doubling time because it is accurate to the computed values here. Okay, because if we start up with 105, that means we double it, it's going to be 210. And 210 is somewhere between 208 and 218. That means it's got to be with a 14th and a 15th month, and we came up with approximately 14 months for the doubling time. Okay, next we'll talk about exponential decay and half-life. Exponential decay and half-life. After a time t, an exponentially decaying quantity with a half-life of t sub half decreases in size by a factor of 1/2 t to the t sub half. The new value of the decaying quantity is related to its initial value at t sub 0 by this formula. The new value equaling to the initial value times 1/2 t to the t divided by t sub half. Okay, similar to the one for exponential growth, but here that exponent is going to be 1/2 as your base. So now in example 11, the half-life of a radioactive substance is 25 years. If you start with some amount of this substance, what fraction will remain in 150 years, and what fraction will remain in 120 years? In 200 years. All right, let's start up with the 150 years. We're told what the half-life of a radioactive substance is. It's 25 years, so that's going to be t sub half. That's equal to 25. And we're starting off with the fraction that will remain in 150 years. That's lowercase t. 150 years. Okay, now the units are consistent because the t half is in years. Our time is also in years, so we don't need to convert anything. They're consistent. So now we're going to use just this factor right here, 1/2 raised to the t divided by t sub half. So this will be 1/2 raised to the t, which is 150, divided by t sub half. That's going to be 25. And if I do 150 divided by 25, that's going to be 6. And I can raise the numerator and the denominator to the 6th power. So if I do 1 to the 6th power, that's going to be 1 over 2 to the 6 will be 64. Okay. Now here they want that as a fraction. So the fraction that will remain in 150 years is 1 over 64. Okay. And then the fraction that will remain in 200 years, well, we got t sub half still going to be 25 years. Here t, this time, will be 200. So we're still going to use that factor of 1/2 equaling to t divided by t sub half. So we got 1/2 That's going to be raised to the t, lowercase t, 200 divided by t sub half, 25. Now, if I do 200 divided by 25, that's going to be 8. So I got 1/2 to the 8th power. Now, if I raise the numerator and the denominator to that 8th power, 1 to the 8th power is still going to be 1. 2 to the 8th power, 2, and then 8, enter, 256. So it'll be 1 over 256. So the fraction that will remain in 200 years will be 1 over 256. Okay, let's look at another example of this. The half-life of a drug in the bloodstream is 18 hours. What fraction of the original drug dose remains in 60 hours and in 72 hours? Okay, so we're told what the half-life of a drug in the bloodstream is. Your t sub half is 18. So now, let's say after 60 hours, okay, that's your lowercase t. And we're still going to use the factor from that formula that I showed you, 1/2 raised to the t divided by t sub half. So here, this will be 1/2. Your t is 60 divided by 18. Let's see, they want this to the nearest hundredth as needed, or to 2 decimal places. So I'm going to go ahead and type all of this in. Left parentheses, 1 divided by 2, the hat key for your exponent, and then that exponent was what, 60 divided by 18? All right, to the nearest hundredth, it will be 0.9, but that 9 is going to bump that 9 up to a 10, so it'll be 0.10. Okay, so here, this will be 0.10. As a fraction of the original drug that will remain in the bloodstream after 60 hours. And then after 72 hours, that's going to be t is equal to 72. Now I'm still going to use that same formula here. This will be 1/2 raised to the t, this time is 72, divided by t sub half, that's 18. And I can do 72 divided by 18, that's going to be 4. So it'll be 1/2 raised to the 4th power. I'm going to do left parentheses, 1 divided by 2, close parentheses, and then press the hat key for your exponent, and then 4. To 2 decimal places, that would be 0.06. So the fractional part of the original drug in the bloodstream after 72 hours will be 0.06. Okay. Okay, here's one more, one more of these. The current, excuse me, the current population of a threatened animal species is 1.9 million, but it is declining with half-life of 25 years. How many animals will be left in 30 years? And in 55 years. All right, let's start off with what we have here. We got the current population of 1.9 million. That's your initial value. Now, they didn't say million here, but I need to convert 1.9 million into a real number. So if I do 1.9, multiply that by 1 with 6 zeros behind it, I'm going to get 1,900,000 written like this. And then we got a half-life of 25 years. That's your T sub half. And we're going to start off with how many animals will be left in 30 years. So your T is 30 years. So in this case here, the new value, this is where that formula comes in for half-life. That's right here. That's going to be equal to the initial value multiplied by 1/2 raised to the t divided by t sub half. Your initial value was 1,900,000 times 1/2 raised to the t, that's going to be 30, divided by t sub half, which is 25. This we can type in the calculator here. I'm going to do 1,900,000 times, and in parentheses, I'm going to do 1 divided by 2, close parentheses, for the 1/2, the hat key for your exponent, and then 30 divided by 25. And in this case, we're going to round to the nearest whole number, so this will be 827,023. That will be the population of a threatened animal species after 30 years. And now for the population after 55 years. Okay? So now T is going to be 55. We'll still use the same formula. We'll just substitute the T with 55 this time. So now your new value, that's the initial value of 1,900,000 times 1/2 raised to the T, this time T is 55, divided by T sub half, that's still going to be 25. So now 1,900,000 times, and I'm going to put 1/2 in parentheses, so left parentheses, 1 divided by 2, close parentheses, press your hat key, and then 55 divided by 25. This will be to one decimal place, to the nearest whole number, 413,512. That would be the population of animals after 55 years. Okay? So that's how we use that exponential decay formula and half-life. Okay, now for the approximate half-life formula. For a quantity decaying exponentially at a rate of p% per time period, the half-life is approximately T sub half approximately equal to 70 divided by P. That approximation works best for small decay rates and breaks down for decay rates up over about 15%. So if it's over 15%, this would not work. But less than 15%, if it's very small, this would work. Okay? Let's look at this example here. example 14. Use the approximate half-life formula for the case below, described below. Discuss whether the formula is valid for the case described. Poaching is causing a population of elephants to decline by 7% per year. What is the half-life for the population? If there are 10,000 elephants today, how many will remain in 50 years? So here we're going to find the half-life of the population. So here we're going to be using T sub half. That's approximately equal to 70 divided by P. Your P is going to be that percent, not as a decimal, just the number in front of the percent sign. In this case, it's going to be 7. So when we do 70 divided by 7, that's going to give us 10. So the half-life of the population will be approximately 10 years. Okay, now the other half of the problem, if there are 10,000 elephants today, how many will remain in 50 years? So our initial value, that's 10,000. How many will remain in 50 years? That's lowercase t, 50. And T sub half, we found that out to be 10 from up here, finding the half-life of the population. So now, the new value is equal to the initial value times 1/2 t divided by t sub half. That's the formula for the exponential decay, or the exponential half-life formula. Your initial value was 10,000 times 1/2, that's going to be raised to the lowercase t, that's 50, divided by t sub half, that's 10. Well, if I do 50 divided by 10, that's going to be 5. So I can say 10,000 times 1/2 raised to the 5th power. And in the calculator, we can do 10,000 times, left parentheses, 1 divided by 2, close parentheses, press the half key, and then 5. And we're going to round to the nearest whole number, as indicated. This will end up being 313. So if there are 10,000 elephants today, in 50 years, only 313 elephants will remain. Now, does the approximate half-life formula give a valid approximation in the case described? It does. Okay. Now, example 15. Here we're going to use the approximate half-life formula for the case described below. Discuss whether the formula is valid for the case described. And in this case here, the production of a gold mine decreases by 8% per year. What is the approximate half-life for the production decline? Based on this approximate half-life, and assuming that the mine's current annual production is 4,000 kilograms, about what will its production be in 10 years? First of all, we find the half-life for the production decline. That's at T sub half, approximately equal to 70 divided by P. And this is what P is, 8%. So P is 8. And if you do 70 divided by 8, it'll be 8.75. So the half-life projection for the projection decline is 8.75 years. And then next, we want the approximate half-life for the projection decline. So the projection will be how many kilograms in 10 years. Our initial value was 4,000 kilograms. And about what will its production be in 10 years? That's your T. T is going to be 10. So here, the new value. That's the initial value times 1/2 raised to the T divided by T sub half. And that initial value was 4,000 times 1/2. Your T, lowercase t, that's 10, divided by T sub half, that's going to be 8.75. And I'm going to go ahead and enter all of that in the calculator. So here, 4,000 times, left parentheses, 1 divided by 2, close parentheses. Hat key for your exponent, 10 divided by 8.75. To the nearest whole number, it will be 1,811. So the production will be 1,811 kilograms in 10 years. Now, is this formula valid in the case described? In this case, our rate was 8%, so it would be valid. Okay? Just like in example 14 that I did. Because if I go back to that, that rate was 7%. It is less than 15%. Okay, and in example 15 that I just did, it's also, that rate was less than 15%. 8% is less than 15%. So here, that formula would be valid in this case described. Okay, now on the next page is the exact doubling time and half-life formulas. For more precise work, use the exact formulas. These use the fractional growth rate, R is equal to P divided by 100. So here, you take your percentage, convert it to a decimal by dividing it by 100. For an exponentially growing quantity with a fractional growth rate R, the doubling time is going to be this. T sub double is equal to log to the base 10 of 2 divided by log to the base 10 of the quantity 1 plus R. And for an exponentially decaying quantity, in which the fractional decay rate is negative, that means R is going to be less than 0, the half-life will be T sub half equaling to negative log to the base 10 of 2 divided by log to the base 10 of 1 divided by R, that quantity, okay? They're both the same, but for T sub double, it's positive. For T sub half, it is negative, okay? So now in example 16, we're going to compare the doubling times found with the approximate and exact doubling time formulas, then use the exact doubling time formula to answer the given question. Inflation is causing prices to rise at a rate of 12% per year. For an item that costs $500 today, what will the price be in 4 years? Okay, so now we want the doubling times found with the approximate and exact doubling time. So I'm going to write this at the bottom. For the approximate doubling time, your T sub double was approximately 70 divided by P. And in this case here, your P was 12% up here. That's what P is. So when we do 70 divided by 12, and this is going to be the 2 decimal places, 5.83. Okay. And then the other part will be the exact doubling time. That's where we use that T sub double formula here. That means R is going to be, in this case, P divided by 100, and it's going to be that 12 divided by 100, which will be 0.12 if you do that on the calculator. So here's your T sub double formula for the exact doubling time. That's log to the base 10 of 2 divided by log to the base 10 of the quantity 1 plus R. Now that comes from this exact doubling time formula up here at the top, as you can see. Now I'm going to substitute the R with 0.12, so it'll be log to the base 10 of 2 divided by log to the base 10 of the quantity 1 plus 0.12 if I have enough room here, log to the base 10 of 2 divided by log to the base 10. 1 plus 0.12 would be 1.12. Now this can be done in the calculator. Now log to the base 10 is the same as the log key on the left-hand side of the calculator. So in this case here, the numerator will be log of 2, close parentheses, divided by the denominator will be press the log key and then 1 plus 1.12, close parentheses, and then hit enter. Now we're going to round this off to 2 decimal places as well. So this will be 6.12. Okay. And if you didn't catch that, here it is again. Log, press the log key on the left-hand side, number 7, and then type in number 2, close parentheses, divided by, and then press the log key, 1.12, close parentheses. 6.12. That's your exact doubling time. And now compare the doubling times found with the approximate and exact doubling time, and you're going to choose the answer below. You can see here your approximate doubling time is going to be less than the exact doubling time, as you can see. Okay. Kind of have to read through those answer choices and pick the one that would best fit what you're doing here. Okay, now for an item that costs $500 today, what will be the price in 4 years? In this case, your initial value was $500, and the T, which is the time, is going to be 4 years. Okay? Now, the new value is going to be the initial value multiplied by 2 to the T divided by T sub double. That's the formula we got through talking about not too long ago. Your initial value was $500 times 2 raised to the lowercase t, that's going to be 4. But for T sub double, we're going to use the exact doubling time of 6.12. Not the 5.83, that's the approximate. We want to use the exact doubling time. because it says here, use the exact doubling time to answer the given question. So here we got 500 times 2, and then the hat key, 4 divided by 6.12. Now this is what I come up with. $786.54. Okay, that's the approximate. That's going to be the amount in dollars and cents to 2 decimal places. Okay, so for an item that costs $500 today, the price in 4 years will be approximately $786.54. Okay. All right, now the last example on this for this video, and I apologize if this is a very lengthy video here. Compare the doubling times found with the approximate and exact doubling time formulas. Then use the exact doubling time formula to answer the question. A nation of 200 million people is growing at a rate of 4% per year. So I know P is going to be 4. What will its population be in 25 years? Okay, so here, let's start off by using the approximate doubling time formula. And of course, P is going to be equal to 4. So T sub double is approximately 70 divided by P. That's the formula that we use. So if I do 70 divided by P, which is 4, I'm going to get 17.5. So in this case here, the approximate doubling time will be 17.5 years. And now for the exact doubling time. Okay, now the R is whatever P is divided by 100. So if we take 4 divided by 100, that will be 0.04. If you do that on the calculator. So the exact doubling time formula, T sub double, that's going to be log to the base 10 of 2, log to the base 10 of 2, divided by log to the base 10 of 1 plus r. So we're going to substitute that r with a 0.04. So we got log to the base 10 of 2 divided by log to the base 10 of 1 plus 0.04. This will give me log to the base 10, log to the base 10, not 2, log to the base 10 of 2 divided by log to the base 10 of 1 plus 0.04 will be 1.04. And that can be typed in the calculator here. So in this case here, if I do log of 2, close parentheses, divided by log of 1.04, close parentheses, to 2 decimal places, this will be 17.67. So the exact doubling time will be approximately 17.67 years. And I rounded that off to 2 decimal places. So here I need to put a 0 for the approximate doubling time here. Now, compare the doubling times found with the approximate and exact doubling time. You can see here the approximate doubling time is less than the exact doubling time. So it'd be that answer choice there. Okay, now, what would the population be in 25 years? Okay, so now I need to move this up a bit. My initial value in that problem, we were given the initial value of 200 million people. So I'm going to use 200 because in the answer they have million people. And in 25 years, they should t. Now we're going to be using that formula of the new value equaling to the initial value times 2 raised to the t divided by t sub double. And in this case, if that initial value was 200 multiplied by 2 times t, your time 25. Now for the t sub double, we're using the exact doubling time as indicated in the directions. That's the 17.67. Because it tells us to use that to answer that question. So here 200 times 2, have t for your exponent, 25 divided by 17.67. To the nearest integer or to the nearest whole number, this will be 533 million. Okay. So in this case here, the population will be, in 25 years, 533 million people. Okay. Okay. Now, I'll admit the homework is going to be quite a challenge. It's going to be quite a lot, so spend a lot of time on this one. If you just practice on this one, you should be okay. All right, this video will conclude on doubling time and half-life.